So we're doing 14.4. This pencil is driving me nuts. It's like the fifth time it's broken today. All right, so 14.4 today we are today we're putting it all together. Heat curves. So it's actually not going to be anything new today. We're going to take a look at a whole bunch of stuff we have been doing or did do last week. We're just exactly like I said, putting it all together today. So here's the type of question I ask in this unit. All right, so how much energy would it take to warm 250 grams of ice from negative 25 degrees Celsius to steam at 150 degrees Celsius? So there's actually a problem that's going to take quite a bit of work. None of the work is exceedingly difficult. Like I said, we're actually not learning anything new today. You did all of this work last week. It's just today we're putting it all together. Good to visualize what we're doing first. A problem like this, again, I know we did it last week, and you might be tempted to say, hey, we're bringing up the temperature of ice by 175 total degrees. But we're not. You can't. Well, you can, I guess, if you start low enough, but you can't when you're only starting at 25 degrees Celsius. So this is not just a one-step problem, which is, I think, where a lot of people get in trouble. We can only warm up ice so much. If we're starting at negative 25, we can only warm up ice up to 0 degrees. So that would be our first energy, our Q1. Then we'll need to melt that ice. That would be our Q2. Remember, when we go through a phase change, we don't have a temperature change. We're adding energy, but we're not actually changing the temperature. We go from ice at 0 degrees to water at 0 degrees. Once we get that water at 0 degrees, now we can bring up the water, but again, we can't bring it all the way to 150. It's not possible. You can't have water, not in its liquid form, above 100 degrees. So this will be our third amount of energy here. Once we get our water up to 100 degrees, now we can boil it. And again, that is a flat line. We're changing state. That doesn't change temperature. So that'll be our fourth amount of energy. And finally, once we get to our steam, we can then bring the temperature up to the final temperature of 150 degrees. So at the end of the day, we need to make 5 energy calculations for this problem. So that's kind of the tricky part. It's kind of the hard part. It's quite a bit of work. But none of the work is all that difficult. We did all these steps last week. We just haven't put them all together, which is what we're doing today. Put them all together. All right, well, nothing to do but get started, huh? Our first energy, Q1, we're changing the temperature. Our formula for that is mass times specific heat. Now, below 0 degrees, water exists as ice. So it's the specific heat of ice times how much are we changing the temperature. So this is our first calculation, our first formula, our first calculation. Our mass all day long today is going to be 250 grams. That's not going to change. We're not destroying mass. Specific heat of ice. Don't know it off the top of my head. Good thing we took notes on it the other day. So specific heat of ice, 2.1 joules per gram degree Celsius. And our temperature change, again, I think this gets a lot of people in trouble here. We're not going from negative 25. Oops. We're not going from negative 25 to 150. It's not possible. You can't have ice above 0 degrees, let alone all the way up to 150. So the only place we can go is up to 0 degrees. Then we won't have ice anymore. So 0 degrees minus negative 25 degrees. And when you subtract the negative, it's kind of like adding. Our temperature change is 25 degrees Celsius. Cool, so we got all the variables. We're ready to plug these in and calculate. $250 grams times 2.1 joules per gram times 25 degrees Celsius per gram per Celsius. Sorry. Grams are on the bottom and they're on the top. So they're on the top, they're on the bottom, they cancel out. Degrees Celsius is on the bottom and on the top, so they cancel out. We're left with just joules. That's a good thing, and energy should be measured in joules. So all we have to do is crunch the number here. $13125. Let's double check our significant digits. 4, 2, and 3. I'm going to be limited to just 2 significant digits in a multiplication problem, but I don't want to round just yet. That'd be the 1 and the 3 is the only significant ones, but I don't want to round just yet. This actually isn't my final answer yet. So what I'm going to do is I'm going to keep at least 2 extras. I'm just going to underline them to show that they're not significant. I'm going to keep the 1 and the 2. The 5 is enough to round up. So I'll say 13130, and I'll underline that second 13 because they are not significant. So there's my first energy change. Again, that's this area of the heat curve right here. I did not have a title on this, so. Heat curve of water, we found our first amount of energy. How much energy is going to be required to bring our ice from negative 25 up to 0? Now we need Q2. Q2 is going to be melting the ice. So that's a little different formula, but we worked with it last week. It's mass times delta H fuse. I don't know why they use delta H fuse for melt. I don't know. I don't know why they can't just use the word melt, but they do. So our mass hasn't changed, 250.0 grams. Delta H fuse. Well, I don't know that off the top of my head, but I've got it in my notes. If I look back, there it is, 334 joules per gram. So cool, this isn't that much of a calculation, huh? All we really to do is remember, or not memorize even, just remember the formula to use, and there we go. Q2 is 250.0 grams times 334 joules per gram. Cool. And grams on the bottom, so it's going to cancel out with the grams on the top there. 250.0 times 334. 83500. Let's take a look at our significant digits. 4 in our mass, 3 in our constant. So we want 3. Hey, that works out well. We have 3 significant digits. The 8, the 3, and the 5. The zeros are not significant unless I put a decimal after them, but I'm not going to do that. So it's not significant. So 83,500 joules. No underline needed. They're all significant. Cool. Cool, cool, cool. So there is our second calculation of energy. It took us about 13,000 joules to get this really, really cold ice up to melting temperature. And then it took us another 83,500 joules to go ahead and melt the ice. Not even halfway home yet, though. Our next calculation, now that we've got our water's at 0 degrees, we need to bring it up to boiling temperature, 100 degrees. So that's going to be our Q3. We're raising the temperature again. So our formula goes back to the first one that we used, mass times specific heat. This time we're working with liquid water and our change in temperature. So it's not really a new formula. It's a formula we used last week. It's the same formula we used in Q1. The only difference is the specific heat of the water this time. Hey, our mass is still 250 grams. Nothing's changed about that. Specific heat of the water, got to look back in the notes. The C of water, 4.18 joules per gram degree Celsius. And our change in temperature, again, if I go back a page and read the directions, I can't go up to 150 degrees, not possible. Water is going to boil at 100 degrees, so I can only go from 0 up to 100. That's it. Don't try to go further. It's just not possible. My final temperature is 100 degrees. I started at 0 degrees, so my temperature change will be 100 degrees Celsius. So there we go, 250 grams times 4.18 joules per gram degree Celsius times 100. Ready to all plug it in. There we go. Again, let's check for significant digits. I've got 4 there, 3 there. I'm actually going to say this 100 is infinite. We didn't really measure from 0 to 100. It's just a known quantity, so there's infinite digits there. So we're limited to the 3 digits from 4.18. That's the 1, the 0, and the 4. But again, I want to carry at least 2 extras if I can. It'd be the 5. I'm not going to round it yet. But I am going to underline it to show that, hey, that is an insignificant digit. I just don't want to round it off yet and have round off there. So 104,500 joules to raise the temperature of our water. Get back to our heat curve. That's this segment of the line here. Now that we got water up to 100 degrees, we need to boil it. So Q4, how much energy to vaporize our water? Again, pretty simple formula, guys. We're not doing, not doing rocket science. These aren't terribly difficult formulas. I think, again, the trick is knowing how many Qs we need to find, how to go about finding them, and having the patience to work through all these problems. So in order to vaporize water, the formula is your mass of water times your delta H vape. Our mass, hey guys, our mass isn't changing. We're not gaining water. We're not losing water. We have 250.0 grams. It hasn't changed. And our delta H vape, that's a constant. Again, I don't know it off the top of my head, but that's why I take good notes. Look back and see, oh, there it is. 2,260 joules per gram to vaporize water. And we've got grams on the bottom. Grams, so grams divided by grams cancels out. We left just 1 on the bottom. We got joules. That's what we want because we're looking for energy. Works out well. Four significant digits, 3 significant digits. That works out well. The 5, the 6, and the 5 are all 3 of my significants. These zeros don't count because there's no decimal after them, so that works out really well. So there's Q4. Oops. There's Q4, the amount of energy to vaporize that water. And finally, last thing we need is our Q5. Now that we've got that steam, that water vapor, we have vaporized that water. Now we need to bring it up to our final temperature. We want to take it to 150 degrees Celsius. So let's calculate that final amount of energy. Same exact formula that we used for Q1 and Q3. And really only the difference is that our specific heat is a little bit different. We've got a unique specific heat for vapor. I mean, our mass hasn't changed. The specific heat for water vapor, 1.9 joules per gram degree Celsius. And our change in temperature, well, we started at 100 degrees, and our question's asking us to go up to 150 degrees. How do I know we didn't start lower than 100? Well, steam doesn't exist lower than 100. So we have to be at 100. We brought it up there. So our final temperature is 150 degrees Celsius. We're starting at 100 degrees Celsius. That last temperature change there is 50 degrees Celsius. Cool. Plug it in and solve for our last measure of energy. Oops. I'm going to put 0.0 here. There's that 0.0 there. So subtraction problem, we want our last digit to be in the placeholder of the smallest, so 150 goes to the tenths. So there's my tenths spot. So 250, 0.0 times 1.9 times 50.0. There's our value. Again, let's see, grams cancels out. Degrees Celsius cancels out. We're left with joules. That's excellent. That's exactly what we want. 23,750. There's 4 digits there. 2 there and 3 there. Oh, sorry. You guys couldn't see any of that? Okay, cool. Awesome. All right, well, there we go. 23,750 joules. And again, I'm going to underline that 7.5. They're not actually significant because of that 1.9. I only want 2 significant digits. But I don't want to round them off just yet. We've got one more step to make here. So there's our last step. We have steam at 100 degrees, and we brought it up to 150 degrees, which is where the question told us to bring it up to. So there we have it, all 5 steps in our heat curve. And the final part is how much total energy is this? Well, pretty easy to do this. Q1 plus Q2 plus Q3 plus Q4 plus Q5. You guys know how to total, add everything up. Our first amount of energy, Q1, 13,130. Pencil. 1, 3 are underlined. Our second value of energy, 83,500 joules. Our third amount of energy is from this page, 104,500 joules. Q4 was 565,000. It's a big one. And Q5, that's the one we just solved for, 23,750 joules. Add all these guys up. I'm going to go ahead and record this answer and then deal with my adjust for my digits here. All right, so there's the raw number right off the calculator. But get my actual total, I need to make sure that my number of digits is correct. So this was an addition / subtraction problem. It doesn't matter how many digits we have, it matters what placeholder the last one's in. It's like this first one here goes to the thousands column. Ones, tens, hundreds, thousands. This one here, ones, tens, hundreds, okay. This one here, ones, tens, hundreds, thousands. The 4 is the last digit. It's in the thousands column. Ones, tens, hundreds, thousands. Okay, I'm in thousands. Ones, tens, hundreds. Okay, thousands. So they're all in the thousands except for this one. We're limited to the thousands. We can't go more accurate than the thousands column. Thousands, 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 hundreds. So we need to go to the thousands column. Tens, hundreds, thousands. Sorry, ones, tens, hundreds, thousands. There we go. The number after the 9 is enough to round up. It always kind of makes it difficult. It means we got to write in scientific notation. Because that 0 needs to be significant. 3 significant digits. Actually, the total number doesn't matter. What matters is that the number in the thousands column is our last significant digit. There it is. So this is one of those odd ones that has to be written in scientific notation. Otherwise, there's no way you could have that decimal right there, that digit right there couldn't be significant without making numbers after it's significant. So kind of a little interesting one there, but there we go. It's about 790,000 joules. That's a pretty good amount of energy. It's a little small, but, well, that's a lot of them. Might as well have a little fun with the colors. There we go. So that's the total amount of energy required to bring 250 grams of ice up from negative 25 degrees Celsius, turn into steam, and raise that temperature to 150 degrees. Questions? Which one? So my Q total? So most of them, the only one actually that doesn't, their last significant digit is in the thousands column. Right, so underline the 1, 3 there. So the last significant digit is the 3, which is in the 1000s column. Same with this one, it's in the 1000s column, 1000s column, and 1000s column. So we can't report an answer that is more accurate than that. So that's kind of the idea with addition and subtraction. Is these are not significant digits, so I can't report something that's more accurate. So my last digit had to be in the 1000s column, which turned out to be kind of a pain because then I had to write it in scientific notation. But yeah, I can't report an answer that's more accurate than my digits allow for. And so that's kind of the reasoning for addition, subtraction, sig fig rules. They're fun, right? I'm smiling big time. You can see it. Good question. Good question. Good question. Other questions? Okay.